Hi. So, to start off with a question. What do all of these headlines have in common? You might have some hints if you were in the keynote earlier. They all involve hijacking BGP, that's Border Gateway Protocol, and that is the rules that decide the best route for data on the internet. So a BGP router maliciously announces that it is the owner of a specific address that doesn't belong to it, and it tricks the other nodes in the network to route data through it. How do you stop BGP hijacking? Well, the short answer is you kind of can't really. There's no catch-all configuration that you can make to prevent it. And so that kind of leaves us with the main tool in our toolbox of encryption, which is all very well and good. You likely know how Hashcat works. You sit there on a network, you capture as many hashes as you can, you set Hashcat running, maybe for a week, something like that, and then you come back to a neat list of correct hashes. Except, in the case of these incidents before, it's now Hashcat with a Q, because all of the coolest quantum tools have a Q in them, and it isn't password hashes anymore, it is the keys to the encryption, and you're just waiting for your quantum computer. That's going to take you quite a while, maybe, an awful lot longer than a week for sure, but some data has a very long provenance. My identity data, my biometrics, for example, they'll still be my identity and my biometrics in 50 years' time if I'm very lucky. So this problem still stands. How do we encrypt our data better? And actually, it's not really how do we encrypt our data better, it is how do we share keys better? Because that is the weak link in this. Some debate for that, but that's for another discussion. And that is exactly what I'm going to talk about today. How do we share our keys better? And who am I? Well, I'm Frey. I'm CTO at Caveri Quantum, where we're doing quantum-safe symmetric key establishment for authentication and identity and access management. And that was after a successful seed fundraise in the summer. And before then, I did my PhD with Ben Varco, our co-founder, working on this technology. And then in the in-between years, I wanted to understand real-world InfoSec, and I spent some time as a tester and an analyst, so I was once sat over there. And I should also add that there are a great many other people who have contributed to this underpinning research along the way as well. So, just to make things absolutely clear, when we talk about encryption and cryptography, we often mean a whole variety of things, and I'm only really going to be talking about one specific part. So for the avoidance of all doubt, I'm specifically talking about sharing symmetric keys. That kind of necessitates me talking a little bit about asymmetric keys as well, because that's kind of how we do things at the moment. And I'm also going to add that this is a talk about crypto. It would be very easy for me to go knee-deep into some maths, but I actually want 90% of you lot to actually be able to walk away from here and feel like they followed 90% of it, and hopefully learn something new along the way as well. And how are we going to do this? Well, we're going to talk a little bit about how we are able to get symmetric keys at both ends, so some existing methods, implications of quantum computers, and then we're going to talk about the two kind of methods we have for quantum resilient key sharing at the minute, and then I'm going to introduce a new method, which is what we're doing. So, if you want to encrypt something using a symmetric key, first of all, you need to make sure that each party has a copy of the symmetric key. And unless you are going to physically pre-share this key, then the two intended parties in that communication must be able to see something that a listener can't for some reason. So this requires us to have some preferential conditions for Alice and Bob, something that allows them to extract something meaningful and mutual that isn't meaningful and not accessible to an eavesdropper. And there's another kind of term we can use for this, and that is that Alice and Bob have to be able to distinguish something that an eavesdropper sees as indistinguishable. something that gives them a difference in their perspective. And there's a reason for me to use that language, because we can borrow from physics here. We can talk about entropy. And entropy is the orderedness of data. And what I have up here, I don't know if you can see the laser pointer very well, but we have two boxes of particles. Those boxes are the same size, and they've got the same number of particles in. And on the left, you have two boxes. At the start, they have blue particles on one side and orange particles on the other. We take the partition out in the middle and we let them mix about. And we can say that the entropy of these two things when they're mixed together is just the same as the entropy of the two things before. We call this distinguishable. We're distinguishing between where the particles came from in the first place. The other side of this is indistinguishable. So this time, we've not bothered labeling the particles. They're kind of all the same. And this time, when we take the partition out, it actually loses entropy. It becomes more ordered somehow. And that might be a bit strange to think about, but if we put this partition back in the middle again, actually, there's no real difference between that and how it was when it started out. Whereas on the other side, if I put that partition back in again, there'll be some orange and blue mixed together. Or we can also kind of think about how we're labeling these. So at the bottom one, on the left-hand side one, we'd have to say, if I was to label those from left to right, I'd say blue, orange, blue, blue, orange, orange. Whereas the others, I'd just say, oh, there's 6 purple. So it's more ordered. And we can link this concept of distinguishability to information theory and information entropy. And actually, we have an equation for this. So all of the entropy that's from the first box, we can call HA, and all the entropy that was in the second box, we can call HB. And if they're distinguishable, then these two things you can think of as and you're talking about the total of both. However, when you think about them indistinguishably, there becomes an overlap there. And that difference, we call that the mutual information. And this is basically where our secrecy comes from. And we can throw an eavesdropper into that as well. So an eavesdropper is represented by this blue circle at the bottom. And if that eavesdropper can see some of the overlapping information, right, then that's fine, she can see some of it. But if there's a region up here that is some stuff that is distinguishable to Alice and Bob, but it is indistinguishable to the eavesdropper, then we have secrecy. And this entire approach is an information theoretic approach, and that underpins one of the methods we're going to talk about. The other one is computational complexity. So we have computers, they're deterministic, they follow a linear set of rules. Some problems are very straightforward, arithmetic ones, and some of them are very difficult. On the extreme end, we have the knapsack problem, which is an NP-complete problem, one of the hardest problems that we have. It's basically, you've got some objects constrained by some parameters, and a knapsack also constrained by some parameters. What is the optimal combination of items you can put in that bag? And we can use some of these harder problems to our advantage. So how we do key exchange at the minute, you'll all be very familiar with this, but we use those harder problems to create these kind of one-way valves between a public key and a private key. So you can't unpick the private key without solving that problem. So Alice can use her private key with Bob's public key, and she specifically chooses Bob's public key in there as well. It creates some function. They can wrap up a series of random numbers, which is going to become their key. Bob can use Alice's public key and combine them to be able to unlock that on the other side. The eavesdropper is there in the middle, and she has her own public key, private key pair, but no matter whose public key she combines her private key with, she can't get the right conditions out. And what's really interesting here is that Alice has preferentially chosen Bob in the first instance. She's chosen his public key to be able to create that. And so this is where we're generating this distinction and this difference of perspective from. If you don't have a deterministic computer, some problems might be solved faster. So if you think about a maze, if we could run actually an electric current through this and image it, and if the one on the left-hand side, that's just showing an electric current going through there, and you can see actually that would solve it pretty quickly. And even if you've got two paths there, one of those is more optimal than the other, it actually takes both paths. But it takes one path more often than the other. And this is kind of more of a probabilistic way of solving things, and we can use these properties of physics to our advantage, and that's where quantum computers come in. We have two main quantum algorithms, that's Grover's algorithm and Shor's algorithm, that are cryptographically relevant to us, that kind of crack some of these problems that we're using for encryption at the minute, or public-private key pairs at the minute. But we don't actually know what sum total of problems these computers are going to solve. So we need some new problems. We can't rely on elliptic curve, and we can't rely on prime factors anymore. Suggestion of one that has been proposed as quantum resilient, given the starting point of some lattice, given a random point on that lattice, and given some other arbitrary point, find the closest basis point to it, except now do it without the diagram underneath and do it in 16 dimensions. And that is a very difficult thing to do. And this actually is one of a number of problems in lattice-based cryptography. That is where the problem that was suggested and standardized by NIST earlier on this year came from. That's called MLChem. But we also have other proposals as well, code-based, that's decoding error-correcting codes, and multivariate polynomials-based. And this basically works the same way as asymmetric cryptography before, except instead of this one-way function being perhaps prime numbers, it's now the new problem instead. So that was our first method of quantum resilient key sharing. What about the second? Well, this is where we replace that communication in the middle by some physical quantum communication channel. And with a quantum communication channel, you only get one chance to measure a quantum state. So Eve can't just copy it. And the most famous of these protocols uses polarized photons. So Alice creates a string R of random numbers. That is going to become the basis for her key. And she wants to send that key to Bob. So she encodes it with some polarized photons. And first she's got to choose, at random, she chooses an orientation that she's going to encode it with, so rectilinear and diagonal. And for example, with that first one, the rectilinear will, combined with a 0, gives you kind of this vertical there, for example, and the others are encoded in a similar way. She sends those over to Bob, and now Bob has to measure them. And for him to measure them, he also chooses randomly what orientation to measure in, which is all well and good, because when Alice and Bob choose the same one, then they get the same number at the end. Bob is able to measure the photon perfectly as Alice intended it. If he chooses something that's different, that photon is undefined in that direction, and so it randomly appears as either a 0 or a 1, with a kind of 50-50 probability. And so now clearly, Bob is going to have some errors in his guess on what R is. And so what they do next is they have a conversation. And with that conversation, they can filter for keeping only the parts where Bob measured the same direction as Alice. And they get rid of everything else. Most discussions on this stop here, but I'm going to take this further for a minute. So let's imagine for a second that Alice sends 2 copies of every state. One of them goes to Bob, and the other one goes to Eve. For Eve to successfully uncover that key, her best bet is to measure all of the states, and statistically, she's going to get 50% of it right with respect to Alice. However, when Alice and Bob filter, Eve will still be left with at least some that she doesn't know about the intended encoding of, because she will have measured differently to Bob. There is no way that she can decide in advance what it is that Bob is going to do. And notice that this entire thing completely turns around if Alice chooses instead to do her filter with Eve. She would create a key with Eve instead. So it is actually her choosing who she does the filtering with that creates that preferential condition, the way to create a degree of distinction and distinguishability between Alice and her intended party versus an eavesdropper. So what's actually happening in QKD is that we're creating correlated data sets. Alice gets a data set, Bob gets a data set which is correlated with Alice's, and they have to filter to keep those bits which are correlated and get rid of the other stuff. The first round, they do this based on that kind of orientation choice. And in the real world, what happens is you don't get a perfect measurement. You get some noise that's thrown in there as well. So there are still more errors that need to be got rid of. And this is called information reconciliation. And we do that, we take some subset and we compare those subsets. We don't say, oh, I've got 2 zeros. You describe something that's more of a summary. So you say, I have an even number of zeros. And Bob also says whether or not he has an even number of zeros or an odd number of zeros. I've not revealed exactly whether or not I've got 2 zeros or 2 ones, but I've just revealed some kind of summary of it. And if they both have the same, then there is a more likely than not chance that they have the same data. And if they both have different ones, then they know that there must be some mistake in there, and they can get rid of them. And so on and so forth, all the way down. And in fact, almost every quantum key distribution method can be generalized to make correlated data sets and now go and filter through those and keep the correlations. And we're just going to look briefly at what an eavesdropper might look like. So this actually allows for an eavesdropper to have a copy of, or a correlated data set as well. So she could have, for example, this string here. So you can see that she has a bit here which is, well, at the top, you know, that is correlated with Alice and Bob. But here she has an error. And she's correlated in some places, but she's uncorrelated in others, just like Bob was. And what she's hearing is, oh, I know that this first pair is even, which means that either I was wrong about my 0, and I have 2 1s here, or I was wrong about my 1, and I have 2 zeros here. But I don't know which one. I have no way of knowing. And actually, for Eve's strategy here, she has to basically create a brute force of every single possible option. And her creating and generating that brute force in the first place is actually that knapsack problem that I was talking about right at the start. And what we have here, if we remember this little diagram, is some part there that Alice and Bob have, which is mutual, that Eve doesn't have access to. And that is why this is secure. It's information theoretic security. Except remember when I said that basically all of QKD generalizes to creating correlated data sets and keeping the stuff that's correlated. Actually, there might be a way that we can create those correlated data sets without needing any physical channel whatsoever. And that is what we are doing. So imagine that you have a signal, and it's broadcasting to Alice, and Eve and Bob both receive it. Both of them have, say, an 80% chance that they receive it correctly, and a 20% chance that they're going to get it wrong. So both of them will be correlated to to Alice with 80%. However, they won't all be correlated in the same place. So there will be times that Eve is right and Bob is wrong, and times when Bob is wrong and Eve is right, and times when both of them are right, and times when both of them are wrong. And in fact, actually, we know that 64% of the time, everyone will be right, and 16% of the time, Bob will be right, and Eve will be wrong. And that, again, is that bit of the overlap in the diagram that we were looking for. And so now they can go on to filter that, so on, and produce a symmetric key. I've used the example of signals here to get this across, but we can simulate this very, very easily. So Alice creates some string of numbers R. It's all very familiar. She also creates another set of numbers A. And that A, the chance of a 1 being in that string is, I don't know, 20%, if we were to carry on the example from before, but it's completely randomly distributed. And we can XOR those two numbers together, and what that has the effect of doing is every time where there's a 1, that bit is flipped, and it becomes noise. It's the A represents the noise in that channel. And so RA can be sent over to Eve. She can get a copy of that, and it can then be sent to Bob. And what Bob does is he also creates a data set B, which has very similar properties to A. It's basically doing exactly the same thing, but it's randomly chosen. A little bit like in QKD, when Alice and Bob randomly chose which orientation they wanted to use. And what this has done is it has created 3 correlated data sets. Eve has a copy RA, Alice has R, and Bob has RAB. And they can now, Alice can now choose who she wants to do her filter with, and if she chooses Bob, she can create some shared keys. We can look at some of the entropy and information theory behind this, and it's quite interesting. So entropy in information theory is directly proportional to the probability. So the probability of Alice having a 0 is 0.5. The probability of Bob having a 0 is 0.5. It's the same for Bob with his RAB. But on the other side of the equation, we have to account for the length as well. We've now doubled the length of R and RAB, so we have 2 times 0.5, which is 1. So now our equation balances out, and Eve has, well, there is no mutual information here, according to Shannon. So what's going on here? Well, this only applies when the length of the string tends to infinity. And that is because random numbers are weird. These 2 strings here, they have been generated from the same unbiased coin. But one of those strings has exactly 50-50 heads and tails, and the other string doesn't. It has something a bit different. So actually, the probability of this one down here is 0.58. So, so how can we deal with this? How can we cope with this? And actually, this is because random numbers are weird in specifically in short strings. So let's think about this. If I have a deck of cards, it's only 3 cards long, and I give you an identical deck, also 3 cards long. If we both shuffle those, there is a 1 in 6 chance that we both end up with an identical shuffling of that deck. If I have a full deck of 52 cards and I give you a full deck of 52 cards, we both shuffle them, actually there is pretty much 0 probability that we will have shuffled it the same way. In fact, some of you will have heard that factoid that if you shuffle a deck, then you are the first person ever in the history of the universe to have shuffled that deck of cards into that order. And basically, if we take a small sample of something, then we have very few ways to order it. And if we take a large sample, then we get exponentially many ways to order it. And this creates our kind of spontaneous low entropy that happens. So, Kolmogorov complexity. Kolmogorov will distinguish between these 2 strings by the complexity of their description. So both of these could have been generated by the same random number generator with the same probability. Both of them are equally likely to happen. We can describe that top one by just saying 10 zeros, whereas that bottom one, we have to say something far, far more complicated. So what happens if, so this is kind of another way of measuring orderedness and entropy. So what happens if one of these is less than the other? or the sum total of these combined when we care about whether or not it came from A and B, is greater than the two of them combined. In this example, we have if I'm caring about whether or not it came from Alice and Bob, then I'd have to say there's 1, 1, and 1, 0, and then 1, 1, and 1, 0. Whereas if I don't care if it came from Alice and Bob together, I could just say there's 2 1s and 2 0s. And that's a shorter way of doing it. And I've created this condition again where we have smaller entropy on one side than on the other, and that means that we must have some kind of mutual information. So we now have a new way to think about our keys and making symmetric keys. So to recap, we take some random numbers R. Alice obscures that with some noise, and she sends it over. Bob takes that. He also adds his own noise to that to create his own independently correlated set. Then they filter and keep the correlations. And for Eve, she gets the copy RA, and she is able to she retains some errors because of this preferential filtering with Bob. In terms of authentication, that's something we need to think about. Well, actually, we can verify that we've had a consistent conversation throughout. If Eve is to get in the way, if she is to change some of those numbers that are being sent to Bob, you can detect that in the probability distribution that Bob has. That allows us to do something where we create a key first. I don't care who you are. We're going to create a key. And now we are going to authenticate. And so this enables peer-to-peer mutual authentication. And we can also, if we want to, integrate this with PKI. So we have created reciprocal Kolmogorov key establishment. We have some kind of overhead, and that overhead actually is mostly in the communication. So if you think about the processing side of things, the most complicated computation that we have done is an XOR, which is incredibly easy for a computer to do. And we also have a way of defining this security. We have that information theoretic approach. And so now it is also quantum safe. And this will lend itself to some use cases more than others, for example, IoT. And that is that from me. So 3 things to take away from here. Secrecy, it's all a matter of perspective. Random numbers have weird properties. And if we take those 2 things and we combine them together, then we can create a brand new way of sharing keys, distributing keys in a way that is symmetric, and it is a far more lightweight alternative. Thank you very much. And if anyone has any questions, you are very welcome to come and ask them. Thank you.
Did I understand correctly that you said that that one security guarantees is dependent on the rucksack problem, or was that just for a specific case of ensuring that, that they matched?
It's not dependent upon the knapsack problem. The security is information theoretic, so there is security there, but the process of Eve's attack in terms of being able to take the what is announced in your correlation filter and being able to figure out, what the most optimal suggestion of what the key might be, that problem of her even just figuring that out is the knapsack problem. But even if you solve the knapsack problem, you still have a brute force that you've got to do, ultimately.
I mean, it's because... And I remember that there's been a couple of attempts at pure knapsack cryptography that have gone poorly.
Yeah.
Is there some sort of guarantee that this is a special hard case of the knapsack problem, or is it just, it's a fun fact that it's extra hard to even get to the brute force stage?
It's just a fun fact that it's extra hard to even get to the brute force stage.
Fair enough. Thank you very much.
You're very welcome.
It sounds like this has a potential to have a lot of network traffic back and forth to get the information.
Sorry, I can't quite hear you. Can you say that again?
It sounds like this has the potential to have a lot of back and forth with the figuring out the shared key there.
Yeah.
For constrained networks like edge devices, you mentioned IoT really briefly. Would this still be doable for those that have very low bandwidths?
So we can kind of balance these parameters a little bit. So we can reduce the length of our keys potentially to reduce the amount of communication that happens. You can also, if you have kind of low bandwidth, I guess it might take a while, but also you can kind of chunk this much smaller. So there's no need to send the entire thing at once. You can send it in kind of little bits and kind of build up a picture of key, for example, with kind of lower bandwidth devices as well.
Thank you.
You're very welcome. Do we have any more questions? No, I don't think so. If anyone wants to come and see me at the end, I also have stickers, so you are very welcome to come and get those. Thank you all very much.